is long, panjang. Kalau blue light, blue light, lambda is pendek. So it's okay. So dia pendek. But since so lambda red is greater than lambda blue. So we see frequency for red is less than frequency for blue, isn't it? Kan? Okay. Alex, lepas tu kan, one thing, tenaga, according to Einstein, E is equals to HF. So H, this one is Planck constant. Planck constant. So F is the frequency. Kan, kalau red light and blue light, we can have intense blue light, intense red light, we can. Tapi for frequency, blue dengan red tak boleh sama. Bukan kan kita tengok kan, because the fundamental property dia punya wavelength ini. So, the frequency pun ikut sekali. So, energy pula, kalau kita tengok, E is equals to HF. So E bagi blue light, what's the relation between E dengan blue dengan red? Is it greater or less than E red? Sebab frequency for red is less than frequency for blue. So, E blue, the energy for blue light
less than E red.
Ya ke? Frequency for red is less than frequency for blue. So apa? Heidi? Heidi, so?
E blue, E blue more than E red. More than E red.
Itu sebabnya kalau kita masak kat dapur kan, it's best that dapur gas kita tu cahaya yang keluar adalah cahaya biru. Because cahaya biru has a lot more energy than warna merah. Okay, if the fire is burning using a red light, means the energy is low. That's why kalau kita nak burn anything, it's best to have the flame color blue. Because it has a higher energy. It can impart higher energy. So if you see your gas stove burning with red light, something is wrong somewhere. Some of energy is gone kiranya. Okay. Alright. Okay, Alex, faham ke the difference between intensity and frequency ni?
Yes.
Okay.
Yes.
Alright. So we go to our experiment now. Okay, so kita nak tengok observation What has they observed? Pertama, they found that current and light intensity is proportional to light intensity. And classical kata, classical ni means scientists pre-Einstein can explain this property. Why current can vary directly proportional to light intensity. Because dia memang ada equation that current can be related to light intensity. And then another property that they found that whenever light falls on this emitter spontaneously, they will see a measurement in the ammeter. Yes, spontaneous measurement of current. Dia tak ada macam delay 5 seconds ke. No. It's just the instant the light falls onto the emitter, then they get direct measurement of current. Yeah, straight away. Measurement in current, yeah. But one thing, yeah, classical couldn't explain these things. I will explain this one later, but this one, I'm just giving an overview, yeah, the failure in the classical explanation. So they couldn't explain, yeah. They said these things should happen after a few seconds. It shouldn't happen instantly, according to them, yeah. They have their own argument why it shouldn't happen instantly. I'll explain later. Okay, next, what they have found is, yeah, a current only when light frequency is greater than a certain frequency. So we call this F sub 0 or threshold frequency. Yeah, only light, yeah, that is higher than a certain frequency, higher or equal to the threshold frequency, can, yeah, allow electrons to be emitted. If it's less, yeah, lesser frequency, there's no measurement in current. The current will be 0. Okay? But classical say, hey, that shouldn't be the case, they said. Because current should occur for any frequency or any lambda. That's why I put it in red, because they couldn't explain it. I said current should always be there, yeah? Regardless of the frequency of light. Whether you use red light, whether you use blue, whether you use green, there should always be a current here. There should always be current flowing in the circuit. That's what people from the classical group says, yeah? But in reality, it doesn't happen that way. So they couldn't explain it. And the frequency does depend on the metal, the kind of metal, whether it's potassium, whether it's sodium. It depends on what material we use for the emitter. Because if you put tungsten here and then you just use a red light, yeah, no photoelectrons will be emitted and the emitter won't register any current. So it does depend, yeah, on the frequency of light. And also what kind of metal do you use here. And then they said, what was found was, yeah, current is constant whenever your potential difference is positive. And current is 0 when the potential difference is equals to V stopping potential. But this one, as being shown in your textbook, yeah, could be easily explained, yeah, by using conservation of energy. So yang ini okay. Classical kata dia boleh explain, ya. Yang the first thing pun sama konsep, ya, that they can explain. But not these two. And next, it says here, the V stopping potential, yeah, the V stop that's measured here, whenever, let me draw here. Okay. Whenever we set this one here to be, no, not negative, this one to be negative, this one to be positive, yeah. So whatever that is being measured here will be negative. There's a time where this one, our current, yeah, I current will be 0. At that particular juncture, yeah, this V will measure something that we call V stopping potential. Yeah, when there's no current flowing, but there's light, yeah, hitting on this emitter, but no current being registered, this V is called V stopping potential.